Look how smoothly Gelo can move if we program it in Python. For comparison, this is how Gelo moves in Scratch with word blocks. You can see he's shaking a lot, and here again is Python and his body is much smoother. With the keyframes we can also make Gelo do very controlled hand plants. So keep watching to find out how I do this. Hi, so cool that you're watching this video. I'm Anton, and in this video I'll show you how to give Gelo here. He's one of my favorite robots in the new Robot Inventor Kit. How to give Gelo here a real natural walk. We are going to use Python, so let's go over to code. Press the little plus here and create a new Python project. And we're going to delete everything that's already there, because we're going to use a different boilerplate. So you go over to my website, and I have done all the heavy lifting for you. So you can focus on the fun part and animating your robot. If you go over to my website, you will find Robot Inventor tutorials, and there the keyframe animation article. And if you go into that article, you can read it of course, but scroll all the way down, and this part here is the part that does all the basics, all the basic code for keyframe animation, and you can just copy it and start working on your robot. It's real simple. In a normal Python situation, you would import all of this. Sadly, the LEGO development environment doesn't support multi-file projects, so we'll have to paste it. Now, we have a new project here, so to say, with some boilerplate code from my website. Let's first connect Gelo over Bluetooth here and start coding. Turning on. Hey, while we're waiting here for Gelo to boot up and connect to Bluetooth, I just like to say that I'm doing all these videos for free, and some recognition here would make me really happy. So you can show your love by subscribing here and sharing this video to anyone who you think this video will be interesting for. Okay, we're connected. Bluetooth is connected. We have the nice green light here, and we have all motor positions. Let's first define Gelo's motors. That's simply creating a list of all motors, and here up there we can see that motors A, B, C, and D are the ones that we need. So let's create them. hub.port.a.motor, comma, copy all this, paste it a few times. Okay, once that's pasted, we can just change the letters here. A, B, C, D. Now we have our motors defined for our program. That's part of every program. What I'm doing different here is that I'm just putting the motors into a list instead of giving every separate motor a name. I find it easier to have them into a list and then go over that list every time in Python and tell every motor what to do. Now, my boilerplate code here works with keyframe animation. So you define positions of a motor and then connect it to a point in time, and then the interpolation that I created and the mechanism classes will do all the magic and move the motors there to the animation you specified. So let's start with creating some walking keyframes. And for Gelo, that is really simple. So it's a list, so I use square brackets here, and inside the list I create tuples, which are a combination of numbers. So I use round brackets there. I could also use square brackets, it doesn't matter much. I think it looks neater with round brackets, but for this situation it doesn't matter much. So You could say that at time 0, the motor has to be at position 0. That's like pretty straightforward. And 0 here is where the gray indicator says it's 0. And at time 1 second, which is 1 second later, the motor has to be at 1 revolution ahead. So it will have turned 360 degrees. This is all we need to make Gelo walk. Just these keyframes, just make sure that the motors rotate at exactly 1 rotation per second. However, not all motors should rotate at the same times and in the same direction, and that's what we're going to define now. So basically every motor has a motor function which is a interpolation, or like it calculates every position between 0 and 360 based on the moment of time, based on how much milliseconds have elapsed. So let's make the interpolation functions here. Linear interpolation of our walking keyframes, and let's make all motors do the linear interpolation here. And so this will use the same keyframes for all motors, and this is already a nice start to see what happens if all the motors are perfectly synchronized and all the motors run exactly 1 rotation per second. Have a look at the model, what this program does. Okay. What we see here is that on one side Gelo steps forward, and on the other side Gelo steps backward. I actually, by default, the program stops after 10 seconds, so let's run that again. And what you see is that on the side that is closest to the camera, the legs run backward. You see them pushing the ground. And so on this side, the legs run forward. What we now have to change is make sure that so this was actually the only leg that ran right, and it's motor D here. So it ran forward in the right direction, where this one also ran forward, but it ran at exactly the same time. And to make him walk, to make Gelo walk, there has to be a 180-degree difference between these two motors. So, and that is here a motor E. So let's start by making the difference here between the two motors. So let's give motor D was right, we won't be changing this. And let's give motor E a time offset of 500 milliseconds. Now, if in a later stage we want to increase the speed here or slow it down, it's easier that we have the period for 1 revolution, that we have it defined as a single number so that we can change it later. So let's define the cycle time for the animation here as a number. Right now we're just going to be using 1000. And for the offset here, we want half the cycle time. So that's cycle time divided by 2. Let's run this program, see what happens. Not much has changed. Oh yeah, on this side the motors have got the offset. I think I changed the wrong motors. I didn't read right. I should have changed motor B. Motor B was right behind D. So let's change it there and make sure that the offset is in the right motor. Motor B is the second one. We are A, B, C, D. So D was right and B should run within half a cycle offset. This will work better. So again, we're looking at motor D here and motor B over there. Now you can see these two motors are already making a nice walking movement, while those two motors are still completely in sync, and we have to offset one there, but also reverse them. So let's do that too. B was done. This one was done. And this one still has to be reversed, so we can give them a scale of -1. This scales these numbers, so 0 and 360, by this factor and effectively multiplies everything by -1. So this will make the whole thing rotate backward. Let's add the scale here too. And then one of these has to be offset. If you look at the model, motor D is opposite motor C, and for a nice walking animation it's best if the opposite motors are offset. So I'm going to guess that motor C here, the third one, has to be offset. Let's try this program and see if we have a nice walking animation. Okay, while the program is loading, it's a nice moment to subscribe. That will really make me happy here. Okay, so here we have it. With just a few parameters here, we have defined a pretty neat walking animation here for Gelo. However, if you look carefully now, what you see is that the feet rotate at a constant speed, and a real dog, if you look at a real dog, it keeps its feet on the ground longer than in the air. So the next thing we're going to try to do is keep the feet on the ground longer and add keyframes to make sure that the part of the movement that's in the air is actually takes a longer time. So for this we'll have to find out where the ground part and where the air part start. So in the video you can see both the model, and in the upper right part of the screen you can see the degrees. Okay, now and then rotate B. Okay, here it starts lifting, so the whole robot sags, then it lands the feet right about here. Let's say the foot lands right about here, and then it starts dragging backwards. So let's say the landing angle, and we are running motor D now, so the landing angle is 340 degrees. So let's say we start our cycle at 340. Deal part. Now let's run our screwdriver until the foot leaves the ground. Here it starts running forward. Let's say it leaves the ground about here. Is 44 degrees. Here I entered the moment where the foot landed. Here I entered the motor, the moment where the foot leaves the ground, that was 45 degrees. And here I entered the part of the cycle time that we want to use for the ground part. That's 0.66 or 66% of the cycle time. And then at the full cycle time, we want the motor to have run 340 degrees where we started, plus another revolution, 360. So let's see what this animation says. Okay, downloading. Time to subscribe and share. I'd really love that. and we've made a typing mistake. This happens if you create lists with square brackets. You have to put a comma after every element, and I forgot to add the comma after my new keyframe definition here. So I added the comma now. Let's try again. Whoa! It's going everywhere. I think we made a mistake. The mistake I made is that I've been looking at the absolute numbers. So if you start at 340 and run forward, you run past 360, and here we get absolute encoder positions in the top of the screen. So this would actually be 360 plus 45. So we started at 340, came to the full 360, and then came at 45, and arrives at 45, and then here we're at the original 340 plus 360. So this should make a better keyframe definition. Oh, this is exactly what we want. So can you see now that Gelo moves his legs quite slowly over the ground and quite fast in the air, and this gives us a much smoother movement. So the legs move a lot, but the body isn't shaking as much. So let's compare this again to the previous keyframes that we have had. Copy this, comment it. So if you press Command / it comments it out. So our previous cycle just went like this. Return everything to the original state, and just for your reference, look at how much the model shakes and how roughly it walks when you just use linear motor movements. So you see how it wobbles and shakes, goes everywhere. Comment these out again, and now compare our new keyframes. That's much smoother in it. Okay, so here you saw a quick demonstration of the power of keyframes, and we can go even further and make Gelo do hand plants with keyframes. So hand plants in Scratch, they are done with model blocks like this, and so you can say that Gelo can put Gelo's legs in trick position and then move for, I think it was about a second, and then you will see him buck. Let's put that in slot 1. So this is the basic jump in stunt in Scratch. Boom! And he actually rolls over. So, and we can do this in Python too, but way more control. So let's now only do the trick position movement here. When the legs move in trick position and the model is in trick position, you can see that it chooses these positions to start with. So that's about 60 degrees on C and about 100 degrees on A, and the others are just the differences. So if you subtract 100 from 360, you get about this number, and if you subtract 60 from 360, you get about 300. That's that number. So the numbers to remember here: 300 degrees for D. What's it? 260 degrees for B. Now let's convert this into Python and create a new set of keyframes that we are going to name stunt front legs at time 0. We were, that's at 300, was it? And then let's just do a full revolution again after the cycle time. 300 plus 360 for now, that's okay as a stunt. And stunt, back, legs, B 265 or 260, and here's cycle time. Let's make that run a full circle, 362. And now let's create new motor functions, comment out the old ones. So the motor functions are now, let's go linear interpolation. For motor D was the front legs and front legs, and let's copy this. Okay, so D was okay. Right, the opposite of D was C, and C should probably be just the inverse. So let's scale it, inverse, and these keyframes here were for motor B, so that means we have to invert motor A. Okay, and then of course we have to make sure that, yeah, it's a bit strange in this motor, the front legs are C and D, and the back legs are actually A and B, because the hub is built in the other way around. Let's have a look at this and see if we can make Gelo stunt. Wow, it worked right away. And what you can see now is that Gelo is keeps moving. So what we can do is just stop the repeating by turning wrapping off. Now that was too much again, we have to tune it back down a bit. Okay, it looks like we found a good solution. So it took me some timing, some tuning, so I speeded that bit up. After some tuning, I arrived to these keyframes. So I did it for the back legs. I just let them run the cycle time, which is about a second. Probably going to work with a real second. And for the front leg, I arrived at 70% of the rotation. We just run at full speed, at normal speed, together with back leg, so 70% of the cycle time, and then after that we traveled 70% of the full rotation, and then after that we just take more time, so the full cycle plus half a second, and in that time we don't even run to the full circle, we run 10 degrees less of full circle, and this carefully puts Gelo in the last bit of the Handplant. So this here is really the power of keyframes, that you can really time the motors and time their maneuvers together to get the results you want. I guess if we run them forward a bit more, Gelo will come down again. So I'm gonna try that after 2 cycles. Make sure that he's back at his original position plus 2 rotations. And let's hold them in place, the back legs. Let's see if at least this gets Gelo back down. Okay, we're up and back down. Nice. We're up and back down, and now we could also extend the time on his head a bit. So I want at the third keyframe I'm on the head, so I can sustain the third keyframe for an extra second here. And that's 300 plus 350, so I'll have Gelo stand for an extra second on the head, and of course wait an extra second until he comes back down. And let's just, well, the back legs, we don't need them much, so let's just add an extra second here. And then also when we are down, let's wait another extra second before doing the next Handplant. We just add this number there again and see what animation we get now. That's a nice and controlled Handplant and the return, and the cycle is over. So this is the full cycle, and we can now turn wrapping on again and make him do repetitive Handplants. Okay, so now we have about 4 cycles for one, so let's start with a 12-second program and see if we get 3 Handplants out of our 12-second program. So again, now is a good time to subscribe while you're watching the finale. 1 Handplant, kaboom! 2nd Handplant, kaboom! 3rd Handplant. That is a full success. Thanks a lot for watching. I hope... Ow! It's running again! It's biting off my fingers! I hope you learned a thing or two about keyframe animation and how to do this with motors. Remember to subscribe and share the video if you think it's interesting, and hope to see you in the next video. Bye bye! Nice! 3 Handplants in a row. Let's try that again.